Okay, picking up where we left off, we just determined using the corner right-hand rule that the force on this particular charge is upward. So I want to talk about what exactly that means, what path this charge is going to take. So at first, you can imagine this charge getting an upward nudge. It's going to start to kind of curve. Let me draw that in for you. It's going to kind of start to go this way as a result. And then if you do the right-hand rule again, you'll notice that the force is now up and a little bit to the left, which will then cause it to curve a little bit more. And if you do the right-hand rule again with this new velocity, you'll get a force that's kind of more up and to the left, which will then cause it to curve a little bit more. As you can see, this force is changing every time the velocity, the direction changes. And it's going to start to kind of go in a circle. This this force becomes the net inward force that is needed for circular motion. If you remember back when we studied circular motion, you always need a net inward force. But at the time, we were looking at a net inward force coming from gravity or a normal force or something else. Now we can see that a magnetic force can also serve as a net inward force. So it's going to curve upward in a circular pattern. So let's take a look at these next three problems. I would like you to try these problems, so pause the video. I'd like you to determine both the direction of the force and then to draw the path that the charge would take. Again, sorry for my lack of labeling. All of the black is representing magnetic field. So pause here, try those, and come back to check your answers. Okay, and here are your answers. Number 1, you had velocity or your thumb up, magnetic field into the page. That leaves a force to the left, meaning that the velocity is going to start to curve kind of up and to the left in a circle. Number 2, your velocity was straight down, so your thumb was down. B is out of the page, giving you your middle finger, your force is to the left. This means that this particular charge is going to go down and to the left in a circular pattern. Then number 3, I just kind of wanted to see what you would do with it. Number 3 is actually exactly the opposite of number 2. So after having done number 2 and getting a leftward force, number 3 is a rightward force. After all, the only thing that's changed is the sign of the charge, being from positive to negative. So let's take a look at the corner right-hand rule with negative charges. You kind of have an option here. The option that I most recommend is to do the corner right-hand rule just like normal. And then right before you record your answer, you flip your answer. That's right, the corner right-hand rule is made to work with positive charges. Just like when we studied electricity, we used conventional current, the positives flowing. So if you want a negative charge moving in a magnetic field and you're determining the force using the corner right-hand rule, do the corner right-hand rule like normal, and then take the opposite answer. Now, technically, you could do like a corner left-hand rule and get the exact same results, but honestly, I don't recommend this because sometimes it gets confusing going back and forth between your right and your left. You forget which one you should normally be doing. Remember, if you're writing with your right hand, it's already an extra step to remember to put down your pencil and do the right-hand rule. So I really prefer to do the normal right-hand rule and then just take the opposite or flip your answer. Yes, you could technically do your left-hand rule too. Okay, I have several more examples for you. For these examples, I would first like you to draw the direction of the force. Then I would like you to draw the direction of velocity. And finally, I'd like you to draw the direction of the magnetic field. Go ahead and give this a try. Pause the video here and come back to check your answers. Okay, so let's take a look at the answers. For number 1, we had part A, the force is down. Part B, the force is into the page. C, the force is up. D, the force is to the right. And then I wanted to talk about E. You probably started to hurt your fingers if you tried the right hand rule with E, because you have your thumb up, but then your pointer finger down. And that's actually not possible to do with your fingers. But I want you to remember what the corner right hand rule was all about. It was about making all of these things perpendicular to each other, or orthogonal. Well, I can already see that velocity and magnetic field are parallel to each other. So this actually would not experience a force. The force would be 0. There isn't a way to make all of those quantities perpendicular to each other. Let's take a look at number 2. A, velocity is into the page. B, velocity is down. C, velocity is into the page. D, velocity is up. And E, velocity is into the page. Number 3, where you're determining the direction of magnetic field, A, magnetic field is out of the page. B, magnetic field is out of the page. C, magnetic field is to the right. I'll come back to D. And E, magnetic field is down. So let's take a look at D. Notice that our velocity is kind of at a funky angle. So your thumb, your velocity, needs to go up and to the right. Your middle finger, force, is still into the page. And we're looking for the pointer finger, the B, or magnetic field, and that's like somewhere down and to the right. As I draw it in, I'm going to be really mindful that, remember, this corner right hand rule is all about making things perpendicular. So I'm purposely drawing in that vector perpendicular to my velocity. It must be perpendicular. So it's down and to the right, 90 degrees from the velocity vector. Great. So I want to talk about when everything isn't exactly perpendicular to each other. For example, here we have a charge that's moving at this kind of angle in a magnetic field. Okay, so we can use our corner right hand rule. The velocity is kind of up and to the right. Your magnetic field is going to be exactly to the right. And no matter if I'm a little bit off between my thumb and my pointer finger, trying to get 40 degrees there, even if I'm a little bit off, I know my force has to be into the page. There's nowhere else for my middle finger to go. So I know the force is into the page. But what if I wanted to calculate the magnitude of this force? Remember, force is QV cross B. So we need to make sure that this velocity, this green vector that we're given, that we're only considering the perpendicular portion in relation to the magnetic field as well as the force. So I'm going to draw in some components here. I'm going to split this velocity vector up into its horizontal component and its vertical component. This might feel familiar from forces. And I know this angle theta, that's 40 degrees. So if I wanted to find, let's say, this side right here, that would be V cosine 40 degrees. If I wanted to find this side over here, I would need V sine 40 degrees. Now, the component that I'm most interested in for this equation is this guy right here, because that component of velocity is perpendicular to magnetic field. And then, of course, you have force into the page, completing all of the perpendicularness. So as I'm substituting into this equation, it would actually become Q V sine theta times B. Or this is what's listed in your data booklet. not the cross product, but this sine theta. And that sine theta is really just coming from the perpendicular component of velocity in this example. Similarly, if we were looking at a current carrying wire in a magnetic field experiencing a force, let's say the current is not exactly perpendicular to the magnetic field. You could again make the substitution for the component. And you could get this equation with the sine theta. Again, just trying to complete the perpendicularness. This is indeed in your data booklet. So let's just put this to the test with what we already know from our right-hand rule. If I were to give you something like this, where you have a charge, it's moving directly up, your magnetic field is to the right, you should be able to use your corner right-hand rule and find that your force is into the page. Now let's use our equation, F equals BQV sine theta. But theta here is going to be 90 degrees. And the sine of 90 degrees is simply 1, meaning that all of the velocity component is already in the direction that's perpendicular to the magnetic field. You can simply multiply B, Q, and V to get your answer. Or the other extreme, what if you had a charge that's parallel to the magnetic field, like we did in our previous example? Your V velocity goes to the right, your B goes to the right, but, well, they're already parallel to each other, so we expect a force of 0. Using our equation, but substituting in an angle of 0 degrees, well, sine of 0 degrees simplifies to 0, so indeed we get a force of 0. That's the mathematical explanation for this example that we talked about before. Okay, so I'm going to leave you with a practice problem. You should do this practice problem before next class, and we're going to start class by checking your answers.